Chapter 6, Lesson 5 of Advanced Algebra, and we're going to continue our work with polynomial equations. And just as kind of a review, we've been working with these polynomials for quite some time now. We worked with quadratics first, and we called them quadratics, not really calling them polynomials, but they are polynomials. And we've done a lot of work with these roots, or the zeros, the places where these polynomial graphs will cross or touch the x-axis, and we've looked at a lot of different ways in how to determine where those roots occur. With quadratics, we looked at factoring and using our calculator to graph them, and we had completing the square, extracting the square roots, and the quadratic formula when we worked with those. When we went to the higher degree polynomials, we looked at some special cubic polynomials that we were able to solve by factoring. We looked at quartics, but again, we had some special cases about where we could use factoring to solve those. But what if we're dealing with those that aren't in those special cases? How do we go about those? Because again, these are very important points when it comes to applying these polynomial equations. So in the next couple of lessons, we want to talk about how we can find these roots of these polynomial equations, and in places where they don't factor. How do we find the roots of a 5th degree, 6th degree, 8th degree, whatever? How can we find these roots? So we're going to talk about some theorems of these roots, okay? Some theorems that apply to these roots that will help us determine where these roots fall. Now, we have, when we were working with quadratic, we had three types of roots. We had the real roots, which actually encompass two. We have the rational roots, which are rational numbers, and then we have the irrational roots, which are the square roots of 3s, square roots of 7s, those types of numbers that are irrational, and all of those rational roots occur somewhere on the x-axis, because that x-axis represents all the real numbers. And then we had those imaginary roots as well, where we have the square roots of negative numbers, which produced imaginary roots. So what we want to look at is, how do we figure out all of these roots if we're not talking about something easy comparatively, like quadratics or these special cases that factor. So the next few theorems that we talk about are going to give us some direction on how to do that. All right. So the first theorem we want to talk about is the rational root theorem. We know that these rational, or these roots, can be on the x-axis, and some of them can be rational. So how can we, or is there a way that we could figure out what those are, or is there something that could help us find those? And the rational root theorem will help us do that. So in this video, we'll talk about the rational root theorem, and then we'll look at the irrational root theorem and an imaginary root theorem. So these three theorems will help give us some direction on how to find or how to locate these roots, and then we will apply what we already know in order to find those. So these theorems kind of give us a roadmap, kind of guiding us as to where we should end up. And once we know where we should end up, then as we take the paths to get there, we'll know if we arrived at the right answer or not, because we'll have some direction before we begin. So as I said, let's take a look at the rational root theorem first in this video. Now, the rational root theorem says this. This is what it says. If P divided by Q, or P over Q, is in simplest form and is a rational root of the polynomial equation a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub 0 equals 0 with integer coefficients, then P must be a factor of a sub 0 and Q must be a factor of a sub n. Now, what in the world does all that mean? Well, let me try to narrow this down. And what it says here, if you have a number that is reduced and it is a root of this polynomial equation set equal to 0, and this is just a mathematical way to represent a polynomial in standard form. You have x to the n minus 1, which represents decreasing coefficients. You have decreasing exponents, excuse me, and then you have these coefficients that go in the same order along with their exponents all the way down to a constant, and if that's equal to 0, it says with integer coefficients. So the only rule or exception really here is that these coefficients must be integers, so there's no fractions. So if these coefficients are fractions, then we can't apply the rational root theorem. Now, there is some algebra we can do with that, but we'll get to that in a moment. If that's the case, then all of the rational roots are going to be a factor of the constant over a factor of the leading coefficient. So if there is a rational root, now the thing to understand about this is just because we're going to be making a list of rational roots doesn't mean that these are roots. It just means that if there is a root that is a rational number, it must come from the list that we're going to make. And this list we can make by using the rational root theorem. All right. So again, what I read probably wasn't very understandable to you, and what I just said in trying to clear it up probably wasn't that understandable to you. Hopefully it was on some level, but maybe an example would work best. So let's take an example. So let's say we had 3x, to the fifth plus 2x squared minus 3x plus 7 is equal to 0. All right, so we're interested in determining the roots of this polynomial. Okay, now if this polynomial has rational roots, in other words, if any of the roots of this happen to be rational number, it's going to have to be, each rational root is going to have to have a numerator that is a factor of 7 and a denominator that is a factor of 3. Meaning, if I take the factors of 7, all the numbers that I can multiply together to get 7, that's 1 and 7. And I put them over all of the factors of my leading coefficient here, which is 1 and 3. All right, and then I put each factor over each other factor. In other words, I put 1 over 1, which is plus or minus 1. And then I put 1 over 3, plus or minus 1 over 3. And then I put the 7 over 1, so plus or minus 7. And then I put the 7 over 3, plus or minus 7/3. What I have here from the rational root theorem is a list of all of the rational zeros that this polynomial could have. If this polynomial has rational roots, and there is no guarantee that it does, at least for right now, then the rational root has to be one of these numbers. It has to be either positive 1 or negative 1, positive 1/3 or negative 1/3, positive 7 or negative 7, or positive 7/3 or negative 7/3. If this polynomial has rational roots, it has to be one of these numbers. If it's not one of these numbers, then this polynomial does not have a rational root. Okay, so that's what the rational root theorem does. What the rational root theorem allows me to do is to make a list of the potential or the possible rational roots of any polynomial. And the way that I come up with the list is I take the factors of the constant, this last value, over the factors of the leading coefficient. All right, and this would be my possible list. All right, so let me give you one more example, and then we'll talk about one more thing. All right, so let's say we had 4x to the fourth plus 3x squared minus 16 is equal to 0. If this has rational roots, what could they be? So I'm going to take the factors of 16, which is 1, 2, 4, 8, and 16. All of those are factors of 16, numbers that I can multiply together and get 16. And I put them over the factors of this leading coefficient, 1, 2, and 4. And so my list of possible rational zeros would be 1 over 1 plus or minus 1, 1 over 2 plus or minus 1/2, and 1 over 4 plus or minus 1/4. And then I take the next number, 2 over 1 plus or minus 2. 2 over 2, which is 1, I already have that, so I don't need to list it again. 2 over 4, which reduces to 1/2, I already have that, so I don't need to list that again. And then I do the next number, 4 over 1, so plus or minus 4, and then plus or minus 4 over 2, which is 2, I already have that. 4 over 4 is 1, I already have that. And then I take 8, so 8 over 1 is 8, plus or minus then 8 over 2, which is 4, I already have that, and 8 over 4, which is 2, and I already have that. and then I do 16. Plus or minus 16. 16 over 1, 16 over 2, which is 8, and 16 over 4, which is 4. So if this polynomial has any rational roots, it has to be one of these numbers. It cannot have a rational root other than these numbers. So the rational root theorem narrows the list down of the entire x-axis, which represents all real numbers and all rational numbers included. It narrows that down to the potential list of rational zeros that any polynomial can have, simply by taking the factors of the constant and placing them over the factors of the leading coefficient. It's my wife waving to me. Hello. Okay, so that's what the rational root theorem does. Okay, now let's talk about how do we figure out then if any of these actually are rational roots. Well, you remember, how do we figure out if something is a factor? Well, we have to divide it out. So we would use, a way of figuring out would be synthetically dividing all of these numbers into this. However, if you remember, there is a theorem that we used earlier that allows me to figure out what the remainder is before I do the dividing. Do you remember what that is? The remainder theorem. So if I take the number 1 and I put it in for x and solve it, that will tell me if I'll get a remainder of 0, or it'll tell me what the remainder is. If I get a remainder of 0, then that would be a 0 of this function. If I get a remainder of something else, then it's not. And then I would do that with negative 1. And then with 1/2 and negative 1/2. And then with 1/4 and negative 1/4. So I could substitute each of these values into the expression and then simplify it, and that would tell me then which numbers are zeros, rational zeros, of the function. Okay? So, a couple of things to wrap this up then. The rational root theorem allows me to make a list of potential zeros of the polynomial by taking the factors of the constant and putting them over the factors of the leading coefficient. And in doing so, that gives me the list of rational zeros. Not that they all are rational zeros, but if there are rational zeros, it must come from that list. And then I can take that list and use the remainder theorem and substitute each of those values in for x, or a, or whatever it is, simplify it, and that will tell me what the remainder is going to be if I divide it out. A remainder of 0 means it divides in evenly, meaning that number is a 0 of the function. A remainder other than 0 tells me that division will not come out even. I will have a remainder, so the value is not a 0 of the function.